In the video we're going to look at an introduction to vectors. First one, the definition of a vector. In general, a vector quantity is a quantity that both has magnitude and direction. It needs to have both. So magnitude and direction. No matter how it is portrayed, it has to have both of those things. If it doesn't have both, it's not a vector. One way of expressing a vector, to show what a vector is a geometric vector, which is basically a geometrical idea. So essentially, because it has magnitude and direction, it's a directed line segment that has a magnitude. So if this is vector R, we would call it R, either a boldface or a bold font R. If you can't do that, you should put what's called a tilde underneath. Some tildes go on the top. You'll see that occasionally. Usually you'll see it underneath. That means vector R. Now it has a magnitude, which is geometrically that would be denoted by the length of this line with the arrow on it, and the symbol for the magnitude of R is usually written like this. So that means vector R, magnitude. Sometimes you'll see the double bars on there meaning the same thing. The direction with reference to some zero is given by an angle theta. So if our reference is made by an axis system, if it's say two-dimensional, we might have what might be familiar to you. It's a bit like the Cartesian axis system. The angle theta would be its direction. So if a vector has both magnitude and direction, what is a scalar? A scalar is a quantity that only has magnitude, doesn't have direction. So magnitude only. So essentially it's any real number. Okay, so basically real number with magnitude only. Magnitude is a word that means size. It's the numerical quantity that goes along with a vector, or it's the only quantity associated with a scalar. So that leads nicely to number 4. Give examples of vector quantities and scalar quantities. So I'll give ones that actually are comparable but contrast. So good examples are to do with things like distance versus displacement. Alright, distance is a scalar. Displacement is a vector quantity. Distance, the direction is irrelevant or unimportant when we're talking about distance, but with displacement the direction is important. And I often like to use an idea if we have a starting point A and another point B, and if we travel in a straight line in a certain direction, let's say there's 50 meters between those two. If you have something traveling straight from A to B, the distance would be 50 meters. The displacement would be 50 meters in whatever direction that's defined to be. So if that happened to be from A to B being to the east, that would be, the displacement might be 50 meters east. You'll see that we won't be using things like east and west, but just as an introduction, you have to have the direction. If we traveled from A to B and then we turned around and went back to A, we would have a distance of 50 plus 50, which would be 100 meters. We would have a displacement, however, of 0 meters. So the displacement would be 0, yet the distance would be 100. That's because whatever direction we describe A to B as, the opposite direction applies on the way back to A. So you've got essentially 50 minus 50. So it's a positive 50 plus a negative 50. Because if that's the positive direction, coming back the other way is the negative direction. Other examples include velocity versus speed. So speed is the scalar quantity, velocity is a vector quantity, for the same reasons as per distance and displacement. Another scalar quantity is mass. Mass doesn't have a direction. However, weight is a vector quantity because it's a force. The weight is usually operating straight down because it pulls towards the center of the earth, whereas mass has no direction. Mass is the amount of substance in a body. Time is a scalar quantity. Temperature is a scalar quantity. Whereas things like acceleration and force, they're vector quantities because they have both a magnitude and a direction, whereas these here only have a magnitude. So those things I've just listed might give you an idea about applications, but in terms of professions that use vectors, you're getting into big ones are things like electronics and electrical trades and engineering. So electronics and electrical fields use vector quantities a lot. They use it so much that they actually don't use some of the same symbols. So because things are in a certain direction, like AC circuits, for example, there's directions apply in terms of phase and things like that. They need to use vectors and many other areas of maths. But anything that uses navigation may use the concept of vectors, such as flight and maritime navigation. Another example is in the sciences and the areas of physics. There's lots of applications of vectors there. And one that's emerged a lot over the last few decades is computer graphics. So computer-based graphics, where you have to make things that look 3D come out on a 2D screen. So vectors are applied there, especially geometric vectors. So the next one, give an example of a two-dimensional geometric vector, and now write the same one as a storage vector. Well, your 2D plane will seem familiar because it's very similar to the Cartesian plane. We will extend it in the near future to the 3 dimensions. But what we call that is the x direction and the y direction, a la the Cartesian plane. There, one unit along the x will give us a vector called I. And we call that the unit vector. So that would be called I, 1 unit. And in the y direction, we have what's called a unit vector j. We'll see this when we get into the Cartesian form. But those two directions can be written in a storage vector form, where the first number is the x part and the second number refers to the y part. So examples, let's have a look. And by the way, I don't mean to suggest that x and y can only be positives. That's not true. We can extend that out, just as in the Cartesian system, to the negatives as well. The values of x and y can be any real number. It is possible. So it certainly can include the negatives. The vector, the geometric vector I've just scrawled in here, it's a bit rough. It's connected to 0, 0, and it goes up to the point, which in the Cartesian plane we would describe as 2, 4, that can be drawn as such. It's a bit rough, the arrowhead's a bit hard, I didn't choose my colours well. As a storage vector, it's simply very much like the Cartesian approach again, 2, 4. If we could please call that vector R, so we would have R is 2, 4, and in a Cartesian sense, vector R would be written as 2I plus 4j. So that means the same thing as that's there as a storage vector. The idea of a storage vector is actually very similar to what you'll learn later in the year called a matrix, but more about that in the future. So there's three ways of doing the same thing there. So 2i plus 4j is the same as 2, 4, and it's the same as that rather shabby drawing that you see there. Redrawn now. Another example. A vector t, you can see to the left there, and let's say that that's negative 2.5 and that is 3.8. So we would write vector t in Cartesian form as negative 2.5i plus 3.8j in Cartesian form, or in storage vector form we would have negative 2.5 comma 3.8, meaning the same thing. The seventh item on the list there is represent a scalar multiple of a vector. Now there are many ways of multiplication operating on vectors. Okay, there's things called the dot product, there's the vector product, there's the scalar triple product, and so on and so on. But at the moment we're only going to focus on what's called a scalar multiple of a vector. It's simply when we get a vector and we multiply it by a real number. So if we look at vector r again, if we multiply that by the scalar 2, we would have 2r, and that means we're getting this vector and multiplying it by the scalar 2, so its components are multiplied by 2. So that would be, it's like using the distributive rule, that would be 4i plus 8j, or in storage vector form 4, 8. Basically that does not change the direction, but it changes the magnitude. The magnitude is actually doubled, and so we have r here, so 2r would actually be twice the length. And as an extension onto that, this is quite optional at this stage, but you think, oh, it changes the magnitude, why doesn't it change the direction? Well, you could turn that, if you know a bit of trigonometry, you can turn that into a right angled triangle, and you see we've got the same proportion of the sides. They're similar triangles, so if we look at the direction there, okay, and we look at the opposite and the adjacent, which is tan theta, it'll be the same angle, okay. So that would be whether it's 4 over 2 or 8 over 4. Okay, it's 4 over 2 for opposite over adjacent for r, and for 2r it's 8 over 4 opposite over adjacent. Remember, tan theta is opposite over adjacent. Okay, opposite over adjacent, which is basically the second part divided by the first part. So it does not change the direction, but it does double the magnitude. We can use Pythagoras' theorem too to calculate the magnitude. Okay, that would be 4 squared plus, 2 squared, which is 4, plus 4 squared, which is 16, and then we take the square root, that would be root 20. once we've doubled it, alright, it's 4 squared, which is 16, plus 8 squared, which is 64. Okay, the square root of 20 is 2 root 5, and the square root of 80 simplified is 4 root 5, and so we can see that it's doubled.